Hello. In this section, we've been talking about proportionality as a mathematical tool for the modeling process. And in this video, we're going to work through an example where the proportionality constant is not actually constant. So what do we do in a situation like that? Well, a starting point is to find k, and that's that slope of that linear relationship between x and y. Find k for each data point, and then find the average. So calculate all those k's, average them out, and that will give you a starting point for the proportionality constant. It doesn't necessarily guarantee it will be the best choice, but it gets you in the neighborhood, and then you can decide whether you need to tweak that value or not. So let's work through an example. So here's a data set that looks at 9 people and their floor to waist length and their overall height. And the values are all in centimeters. And so the question is there a proportionality between these two? The idea being is that if there is a proportionality, then you could use one measurement to predict the other. So what we need to do then is to consider this our x and this our y, and we're going to assume that y equals kx. And we need to estimate k then for each one of these, which of course is just y divided by x. And as we can see, the y is always larger than x, so we expect k to be larger than 1. And if we do that, we get the following table. And so notice in this column how the k values are all around 1.6. There's a 1.76, and a 1.59 is about as small as they get. So if this column was completely constant, then we would have a perfect proportionality. If these values were all over the place, more than they are, then we might have to reevaluate our assumption. But because these numbers are relatively close, we can find the average, which happens to be 1.67. And then we can use that to form a model and see how good of a job it does. And that's what our fourth column here shows, is we take each of these floor to waist lengths, multiply by 1.67 to get a prediction. And then we can compare each number and see how good of a job the model did. So here we're about 8 centimeters off. Here we're about 5 centimeters. Here we're only 1 centimeter, 1 centimeter, 1 centimeter, 1 centimeter there, 9 centimeters there. So overall, not too bad. Again, from a percentage error point of view, all that would be less than 10%. We'd like our model to be better than that, and it is. Another way to look at our model is to graph the data points. And so here's a graph of all the data points, and we can see the non-linearity of the data, that it's not perfect, but the line does fit the data relatively well. Now don't be fooled. This may look like it's not proportional because it may appear that the y-intercept is nowhere near 0, but notice that our x-axis starts at 90. And so if we continue this slope all the way to 0 centimeters, sure enough, our orange line will cross through the origin. So that part is okay, even though it may not look like it from the graph. So overall, we would say this is an acceptable model, even though it's not perfect. But unless we needed something more precise than something like height and comparing heights and other distances of the human body, we would probably accept this. And that's it for this example. We'll see you in the next video.